Thank you, Prof. Good afternoon, everyone. I think I know you all, but I'm presenting something on system dynamics in my entire life. This is the first time, so bear with me. And I am a student of system dynamics. I'm saying that for two reasons. One is I'm really a student, and number two, if I make any mistake, I can get by saying that I'm just a student. Yeah, honestly, I started learning about system dynamics probably 3, 4, 5 years ago, and I'll show you some applications in civil engineering. I think in your field, they are pretty rudimentary, but still I would like to show because we have to start somewhere. And I want to acknowledge Mike Radzicki.
You need the mouse.
Yeah. This one is non-responsive, actually. Let's see. Yeah. So Mike Radzicki, Khalid Said, and the very friendly and helpful SD group here at WPI. Every day learning something, and also learning with Fred, who has joined the PhD program in civil engineering. Uma and Ram, who are also doing their graduate work in civil engineering and trying to use system dynamics. So what I'll do is I will talk about some background issues that require probably the use of system dynamics in civil engineering. Hello, how are you? And then talk about some problems, because as I hear often, and I told you I'm a student of system dynamics, and now I'm really a student because I am auditing Professor Khalid Said's course. So any mistake I make, I ask for forgiveness and do correct me. So problems that we have that need to be modeled, and I hear this often, that system dynamics is probably should probably be known as problem dynamics or modeling problems, and not system dynamics. But we do have problems, and then I'll talk about more problems. And you will see that in civil engineering, we deal with infrastructure. And if you have been reading the newspapers or listening to radio or seeing the TV, I'm sure you're aware of the many problems that we are facing for the infrastructure related issues that we have in this country. And then I truly believe that system dynamics is something that has come to the rescue and that can be utilized for solving a lot of issues. And I know there are other kinds of modeling as well, like edge-based modeling. But my education and my learning in system dynamics has just started, and I do believe that pure system dynamics is really an amazing thing that can help us. And then I'll go over some models. I'll spend most of the time on some models that I have built over the years. And again, in system dynamics level, they're probably rudimentary. And in some cases, you'll probably see that they're more representative of object-oriented modeling rather than actually using system dynamics. But I do hope that you will see why what we are doing that. Now, when you talk about engineers, this is what we do actually in reality. So there's a very simple flowchart that we show a student. And it's a very simple thing. If there is something that should be moving and it's not moving, you use a duct tape. And it should not be moving and it's moving, you use not moving, it's use WD-40. So that's the essence of engineering. And you know, Charlie Chaplin said that life is a comedy in long shot and a tragedy in close shot. And so now when you get into nitty-gritty details, you'll see where we have the issues. And this is what civil engineers do, and people think they do, what I think I do, and what society thinks I do. But what you really do is look at the city or the urban structure, rural areas, ports, railways, everything, and then work in different areas. And if you go to our department, for example, you'll see there's a board which gives the names of different faculty members, and it says transportation, soils, hydraulics, so on and so forth. But in reality, you understand that when you're living in this city, we are not really going into transportation thinking that I'm now going to transportation. It's a seamless world, and one goes into the other. So you get up in the morning, you drink water, which is coming through water system, and then you go out and take your car, drive on the road, which is transportation system, come into buildings, it's infrastructure, which is part of building systems. So, it's a seamless thing, and we try to work on different areas. And I'll particularly concentrate today because I work with roads as one representative component of infrastructure, roads. And I don't have to tell you that roads are very important for survival and for the development of any country. But there are issues that come along with roads. So, for example, if you try to build a 6-lane highway through Brazilian rainforest, Amazon rainforest, you're killing the environment, you're killing the world, right? So I'll touch on those issues also. But the fact of the matter is that you cannot survive, you cannot develop as a country unless you have good quality roads. But you actually harm the environment in a terrible way when building roads. So that's the critical issue. What do we do? How do we work with these things? So background. I wrote in the abstract that civil engineers do not study system dynamics. Not at all. I haven't seen any civil engineering program that has system dynamics, right? Keeping that in mind, if you look at the bullet, it's really a dangerous job because we don't know the connections, we don't think about the feedback loops, we don't think about the long-term impacts in general, but we do make decisions regarding our infrastructure, and the infrastructure we live influences our lives and decisions. I think somebody said, I forgot who said, that we design these buildings, right? We think we affect the design of these buildings. And then the buildings actually start affecting our lives because they affect our thoughts. If it's a closed environment, then you think that way. If it's an open environment, you think different. So it's a dangerous job, not knowing system dynamics, I think. And particularly when you have billions of dollars, which attracts more users, it's faster, and which requires us to invest more. So if you build a good road, people will come and drive on it. They will deteriorate the road faster, and then you need more money. So I see feedback loops everywhere, and that kind of warrants the use of system dynamics. And then if you look at the last bullet, cumulative and dynamic effect of increasing traffic and costs and stagnation in building new roads. And we have some data. I'll show you some data. Since the late 1960s, we have not built a lot of new roads, but the number of vehicle users, number of trucks have gone up exponentially. And we have not invested extra money, but the cost of materials has gone up. Right? So you can figure out what is going to happen. This is the public, just to give an example, what kind of money we spend. So for highways, we spend $165 billion in 2014. That's a lot of money. And if you look at other things, it's the highest amount that you spend as a public funded entity. And but if you look at the public spending as a share of GDP since 1956, you see here it is fairly constant. It has not gone up. Keep in mind that the costs have gone up 100 times, 150 times if you do the math from 1996 to 2011. So the net effect is that we have less amount of money today to fix the roads, fix the bridges, and everything. How do we deal with this kind of thing? So very poor conditions. If you look at different entities that you have, different report cards that you have, you see road fields and dams are in very poor conditions. Not enough money to address maintenance issues, not enough money to address rehabilitation issues, and no adequate public transportation system to reduce the load, at least in the US. And there are some things that we can look at to understand this. Now, I quickly want to make a note regarding maintenance and rehabilitation. So there are two issues here. If you think about buildings or bridges or roads, the regular work that we do to make it livable or make it functional is called maintenance. But at a point when we need to enhance the capacity of a road, so for example, you build the road is functioning fine, but suddenly you have this apartment complex coming up or Walmart coming up, and you'll have more users. So you need to increase the thickness of the road. That's rehabilitation. Okay. And in most cases, we don't have money to deal with either one of these. I hope this thing works, but see, I thought if I clicked on it, it would go to this website.
Yeah.
Yes. Because that's the way I have most of the models. All right, so can I launch any one of these and see what happens? We have Google Chrome. Oh, you have to have the Google Chrome. Really? Let me try something else. What's your web browser here?
I
Yeah. Right. Do you have Firefox here?
go to programs, but
Should I download fast? No, that will take a long.
if it is
Okay.
allowable, but it
Yeah,
doesn't take time, I guess.
yeah, it is allowed. You're right. There you go.
So
No.
if you click on the Windows, will it change on the window icon there? In the lower left, yes, will it show the programs?
There's an Internet Explorer.
No, there is no.
At the top, there's an Internet Explorer.
That's
Yeah.
fine. My only concern is that I should be able to show the models.
Can you? I
Right.
think you need to download
Download.
for Firefox.
Yeah, I think it will work.
So sometimes you have run
Just
issues.
see what
with,
happens.
you cannot install anything without having permission.
Not every.
Let's see.
It
You
says
can install.
The fox should be able to sneak in.
excuse me.
It's like everybody is not happy with that Explorer. Whenever you click, it
It
says
says you should download
the latest.
the latest version. Let's see. Don't impose. Okay.
Now if I click on views,
You have already copied that. Just paste
Just
that.
paste the link.
Just paste that.
I think go
Just
to
paste the link on the
in mine Firefox.
Firefox.
yeah. Let me do one thing. Instead of doing it this way, let me sit down.
Yes.
I can show you, and then I'll get what I need to. So this kind of shows you in a snapshot how you use the civil infrastructure before noon, right? So it's 6 a.m. Drinking water or coffee. You need the energy. The heater kicks on. Then you take a shower. Then you go out for the park or recreation. There's a school building. You need the roads for bus and everything. And you come to office or you take the train. 10 o'clock. Energy, transit, and then solid waste, aviation, ports, and roads help you to get the mail. So by noon, you have used all these things. If you look at the report card of all these different things, take a look at the report card, the GPA. So this kind of tells you the story in a snapshot that what are the conditions of the different components of our infrastructure. So if you look at bridges, for example, that's a C+. The roads, actually it's a D. Okay. and D is the lowest that you have in this table. And so it's a pretty bad situation. So here is the question: that how do you solve the different things with regard to money and construction and the environment, and still maintain a healthy infrastructure? So let me move on to the next part. So how are these things affecting the lives, current lives, and also in the future, right? So everywhere, if you talk to, for example, truckers, right, movers, they would like to carry more goods in their trucks so that they have to make less trips. Why can't they do that? Because the roads are not sufficient to carry a lot of goods. They're not strong enough. And what happens is, if you cannot do that, that means you have to make more trips, which means truckers have to stay away for longer periods of time, they have to drive more fatigue, and actually the road safety is compromised because you and I all share the roads with the truckers. Right? So that's actually a terrible thing. Then the next thing is that if you have a situation like in South Carolina, flooding due to extreme events, you don't have the budget to fund the repair, to fix the road so that people can actually travel to go to jobs or go for schools or hospitals or anything like that. Okay, so two critical things I wanted you to keep in mind how they affect our lives if we don't have the funding to fix it. Okay, so system dynamics.
We have a question here.
Go ahead.
A random question.
Yeah.
So you speak of that. I'm just curious. Does civil engineering deal with snow removal and other things like that on the roads? Or is that another?
Yes. No, that's the same. So snow removal comes under DOT, Department of Transportation, or DPW, Department of Public Works, if you are in a city or town. And that's a good question because last year or year before that, I think Boston, the city of Boston, had spent all the money for salt by the middle of week. They didn't have anything left. So that's a huge thing for any region and Northwest as well. So I think you are familiar with all these things, and I'm not going to repeat them. But from my perspective as a civil engineer, these are the issues that actually are very unique in system dynamics that are required for civil engineering for solving many of the problems in civil engineering. And particularly if you look at the last point, which is reaching consensus, you must have been hearing all the issues and debates going on in Congress regarding the highway bill and what not to do and what to do. So it's a terrible issue. That reaching consensus is a big deal. Everybody has a concern. Everybody has a point, but whose point finally wins? Sometimes it just depends on who has the loudest voice. Right? So that's an important thing. So now I'll switch on to a few models and results. And again, as I said, I'm a student. If I made a mistake, correct me. And hopefully this will generate some interest in you, and we can have some collaborative work in the field of civil engineering. So I'll start with a simple issue, the overall state of the infrastructure, the problem, the models, the results. So I'll show you the problem that I perceive, and then I'll show you the model which is in a server, Stellar model, and then I'll show you some results from that. So here's the problem that we have. We have an aging infrastructure. What I mean is that built in the 60s, there are many infrastructure components, for example, roads and bridges, and they have aged considerably. We have increasing number of users. Population has gone up significantly. Cost has gone up, as I explained, and decreasing budgets because you have other priorities as well opening up. So we have a deteriorating infrastructure, which is as a result of shortfall of budget and the rise in the cost. And every year you will see that the budget shortfall is increasing, billions and billions and billions of dollars. Trying to model this in terms of road infrastructure. So let me see if I can. I don't think it will happen. Again, have to probably. No, it happened. Good. That's excellent. Let me use this.
Yeah.
All right, never mind. I think this way it will take forever. Anyway, so yeah. So what I'm going to do is I'm going to take a look at the models. So these models are there in the server, and hopefully you'll be able to see this.
The software might be limited.
Which software? Yeah, you don't have scale line.
No, not in this.
Yeah.
But I have in my laptop.
It's okay. I can explain.
Oh, can you refresh the page from the top?
Yeah.
It's probably.
It's not set.
And now try again the zoom in or zoom out. Compatibility view. What is the compatibility? But click the compatibility.
Yeah, I think what I need to do is probably actually physically move it like this.
Yeah.
But what yeah, and I can go like this. Yeah. That's okay. I can explain. And I hope this thing cooperates because without the space bar I'm doing. Okay. So what I'm trying to show here is the construction of new road. Okay, so there's a rate of construction of new road, and that leads to new roads. So bear with me. There's a life of the pavement, which is related to the rate of deterioration of the pavement.
You're probably in somewhere in the screen. That's the same.
Because this thing is sometimes falling asleep. Yeah, there you go. All right. So roads needing rehabilitation, there's a rate of rehabilitation. And there is a cost of construction per mile of road. There's available funding, there is a cost of road rehabilitation per mile. Available funding, there's a percentage of roads in good condition. So that public safety and mobility indicator is a critical issue. So you saw the AC grade B that was given to roads, right? So that's based on how safe and how mobile your inhabitants or citizens are. So that's a reflection of the overall quality of the infrastructure. So there's a rehabilitation budget shortfall. There's a vehicle mileage. So if you look at this, I cannot go this way, but the vehicle mileage has been going up. And the vehicle mileage has been going up exponentially. There's a negative change from climate, negative effect from climate change. Typically, the pavements that we drive on, the roads that we drive on, the bridges that we use are dependent on the maximum pavement, maximum air temperature as well as rainfall. Okay, so I'll show you what are those effects. And materials cost has been going up, right? Percentage change. All the models I have the diagrams.
So you're using NetSim.
I'm using NetSim, right?
Actually, you're more advanced than I am. technology because I've not used it.
Just to make sure that I can use it independent of the scale.
Yeah.
So what has happened is, over the years, and this kind of relates to universities also, over the years, the investment in research and also in faculty hiring, for example, investment in faculty, for retaining faculty members or giving them research funding from NSF or the DOT has gone down significantly as the needs of other things have increased. So, for example, now you have more funding going to things like cybersecurity, for example. You have things going on with robotics, for example, but not so much for civil infrastructure. Okay, and the way this has been framed, the issue is that when you have a number of faculty, that kind of indirectly dictates the number of graduates in road engineering or pavement engineering. That dictates the number of researchers in pavement engineering, and everything is dictated by the research funding per year. Because if you don't have research funding in engineering, you're doomed. You will not get any new faculty member. That's a reality. However, whatever way people put it, that we talk about teaching, and teaching is of primary importance. If you don't have research funding, you cannot get faculty members. And what has happened is, it has been shown earlier that the research funding per year dictates all these things, and that actually dictates the change in the construction cost. So actually, when you develop new technology, you bring down the cost of construction. When you develop new materials and new technologies, you bring down the cost of construction, as well as you prolong the life of the infrastructure component. So you have more durable materials. Okay. And if you continue to do this, what will happen is you will see that these things are tied to the rate of change in rehabilitation cost and the budget needs. And finally, it dictates that what kind of public safety and mobility indicator you get. So instead of getting lost here, so I now don't have the little black arrow to go to. So let me start it from the beginning in order to show you the results. If you try to simulate it, so hopefully this will work. So this is like a dashboard, and if you have a research funding of say so, right, and I can go to any level of research funding, and if I run it, look at this plot which shows the public safety and mobility indicator, what is happening over time, and look at the rehabilitation budget shortfall. Okay, so your public safety and mobility indicator drops significantly, and your shortfall increases, and that's the story that we have seen. That's reality. From the 50s to the 2011, 12, 13, 14, the condition of roads have steadily gone down, and the budget shortfall has increased. Right. The question is that how do we fix it? This is not a complete model, and as I said, that there are many things that can be done to improve this thing. But trying to frame it this way, whether it's responsive to critical things, right? So if you see here, there is a yellow, which is a caution. And of course, if I bring it down to very low level, and if you run it, you'll see that this is actually at some point going down further, right? And if I make it 0, which means that I didn't add any research funding now, it has remained the same over the years, and you can see here that it starts to red. But anyway, and of course, you can change it, and you can run it with different numbers, and you'll see that you don't have that much shortfall. Of course, you can keep on increasing that. And in this case, it falls down to a value of 67, whereas at 0 or this level, it fell down to about 45. Okay. You can keep on playing with these things to develop the equations and these things. But the sad thing is that we don't have this model, we don't have this picture in the mind when we deal with infrastructure issues. Any question regarding this model?
This is intriguing. In my mind, never connected the condition of infrastructure to R&D funding and how that draws in the human resources into that area. So this is new.
Yeah, sadly, we have seen data that shows that if you do a research with X amount of dollars, the benefit that you get out of it is somewhere from 7x to 500x. So this is the most effective way of combating the problem. And the problem is there. Cost of materials will increase. Vehicle users will increase. Population will increase. And budgets are never going to go up because you have other things to take care of.
But it also says that drawing more people in for training. Once they are trained, are there budgets to hire them already? That's in the model.
You got me. No, it's not in the model. There should be in the model. So the way I looked at it is that if you have researchers in the universities, you develop new concepts and materials. If you have more trained engineers in this area, then you have more people to implement those ideas in reality. If you don't have the development and the implementation, then nothing will happen. Actually, it will backfire because people will say, oh, you have been spending 10 years developing this thing in the university. Nothing comes out of that. Who cares? But the sad reality today is that, in fact, we don't have enough funding in the DOTs to hire people who can actually go and put this in the field. So, yes, that's a good point. I should be thinking about it. There should be funding for hiring.
Because if there's no funding for hiring, the graduates don't get jobs. That means fewer are drawn in to the schools. So there's another feedback there.
That's the latent structure that is working against them.
Is this happening that the students don't enroll in civil engineering courses already?
Civil engineering has a very steady enrollment. It goes up a little bit, comes down a little bit. But what happens is many of them after graduation are going for construction project management or going for Wall Street, for example, investment and things like that, which is not a bad thing because you learn the analytical skills and you go for those things. But the problem is that, like Professor says, that you don't have lucrative jobs which can compete with other kinds of jobs. When I came for graduate studies in 1991 at Auburn in Alabama, we were 12 people, and that was 91, 92. And if you recall what was going on that time, out of 12, 2 of us only remained in civil engineering. All of the others actually did their masters, took a bunch of computer science courses, and then they started learning C, Java. C was hot that time, and all of them moved on to computer science. So that's the reality, and exactly the problem is that you don't have jobs that can actually lure them and tell them that this is a good job. But
you have a question?
Going off that, when I saw your model, I was also thinking of both of your graduate students are international. So it's also another player involved where the graduate students or students might not be American, and we're talking about America right now, right? Or just in general.
In general, yeah. If you look at this picture is being repeated more or less in every part of the world. In some countries, it is lagging by 25 years. It's coming. There you have major development in roads, people giving out, governments giving out licenses and slashing down duties to make people buy more cars, roads going down faster, and then 25 years the situation will be the same.
It's even made worse by the increased urbanization.
Oh, yeah.
That's either been mandated or promoted by other reasons, right? So now you've got city infrastructure being pressured even more, especially in cities that already have ancient infrastructure for water, subways and roads and so forth. It's an accelerating issue. I had one question, by the way. Intuitively, in the lower right corner, I would have thought that, all else aside, that given the factors that you mentioned, that public safety would look more like a convex function. In other words, it would start declining and then more rapidly decline at a very precipitous rate as the funding shortfall got bigger and bigger and the demand kept getting bigger.
Right. You're right. And actually what I have is a safety and mobility lumped together. And that's actually you can play with the form of that equation. But what I have is this is actually a reflection of how much roads you have in poor condition versus how much roads you have in good condition. But you're right. I have some other models which will actually show you that.
Another question is that what are the implications of the deterioration of the public safety and mobility status indicator? Wouldn't that go somewhere and influence policy decisions? And
It has not been. I mean, ASC has been coming up with this kind of statistics since the last 10 years, and it is not going anywhere because you don't have enough money. Just very good.
another question is that now as you increase the funding, you're just pushing the problem forward. Wouldn't that call for like something fundamentally different in
Yeah, disruptive
infrastructure?
technologies. You need disruptive technologies to totally think about different ways of building. So, for example, building roads. So, for example, if you go to, let's say, for argument's sake, flying cars, you will not need that many roads, right? But you'll still need probably roads for goods, for trucks, because I can't imagine flying trucks for some reason. But you will need ports. Actually, ports are dredging more and more because they're actually experiencing more traffic.
Regarding goods, wouldn't be the old model was trains, using trains, now the trucks, but this Tesla pipe, if it is
Yeah.
used to transport goods, wouldn't
Sure.
that change
Yeah.
the
Yes.
game for the trucks?
If that happens, then we don't need all these things. But right now, 80% of the goods are transported in the US by trucks.
Which also brings the same point to the funding of research, because innovation and disruption could happen when people do research, but now they're like trying to catch their breath to solve the problems.
Yeah. Yeah.
That's the mentality now, is firefighting.
Right. Either way, you need more research to develop more technologies. But Christine, going back to graduate students, I have other grad student, Ryan, who is actually a US citizen. And fortunately, he wants to have his own company after he graduates. He's doing his PhD. So that's a glimmer of hope I have, that he's learning about new technologies and he wants to go for business in the area of road technology. But that wouldn't have happened if there was no research.
I was also thinking about a relationship between the condition of infrastructure and growth rates. I lived for many years in Bangkok. The oldest road in Bangkok is called New Road. That was the first road that was built in Bangkok, and that was very new at that time. And New Road was built for the motorists, which were new at that time. And it was built to connect the river bank, it's on the Chowkia river bank, to the city center. At that time, it's a short distance. At that time, the travel time for that particular trip was like 30 minutes, 40 minutes or so. So New Road shrank it to about 5 minutes. And now there are many more roads built since then. The travel time between city center and Chowkia is still 30 minutes. Because the growth in traffic. So there's a positive feedback there, which always might create the loading on the infrastructure.
My friends
It is.
My friends from Thailand said when they drive in Bangkok, they don't even have to press on the accelerator.
They float.
I've driven there, and I can understand that.
I saw in Sri Lanka, I went there in 2013 for the first time, and then I went last summer. Within 2 years, you cannot believe the same situation. The number of cars have gone up exponentially. It's like crazy. And earlier I could smell the trees and the flowers. Now you can smell only the gasoline. Because they had a 300% duty on imported cars. Now they have slashed it to like 50 or 70%. And they have special concessions for government people for imported cars. So it's the same story. So I don't know. But
This is a random thought because I was just thinking about driving and I think like rerouting. So because of GPS and Google in shortest time, because we know real-time traffic sometimes, or real-time traffic. Is that affecting the roads a lot more because people are going down more unused or typically unused roads?
Okay, yes, they are. But one thing I should mention is that your car weighs probably 1,000 to 2,000 pounds, right? One axle of the truck, fully loaded truck of a truck, is 18,000 pounds. So the damage that a car causes on a highway is minimum compared to a truck. It's actually the trucks and the environment that causes. But that is true because if you have more cars sharing the road with the trucks, then they are standing, they're causing traffic jams, and then you have deterioration also. But that, yeah. That's true.
This is quite another argument for a more integrated transportation system analysis, because a lot of additional freight has been moved onto trucks because a lot of rail has been occupied by moving oil. So truck traffic is going up just because of dislocation between modes of transport. And the rail system in the U.S. is pretty stressed already. I guess more of an academic question about how civil engineering departments think about simulation and systems analysis. I mean, in civil engineering departments, I've sort of interacted with in the past. There'd be divisions for hydraulics or water management, division for structures, something like you described before. But I've never really encountered, as you described, a division for infrastructure systems or total system, urban systems, anything like that. With urban management, that's entirely different matter. But although I've seen some computational specialists in civil engineering departments, it's never been one of those things that was sort of the tip of the spear, for the department. Do you see that changing? I mean, it seems like there would be a natural intersection between, say, civil engineering and systems engineering, for example.
You're right. MIT, for example, has a group, systems group, related to civil engineering, but they are never the tip of the spear. That's a good way to talk. I don't see it happening. Unless we have a lot of collaboration and a lot of effort, because the funding is steadily eroding from civil engineering. And unless there are some technologies that are completely new and disruptive technologies, it's very difficult to have that. Although it's not a very resource-intensive thing, if you think about it.
Right.
So, sorry, I just have the problems. I don't have the solution. But that's a good thing because it's a job security in some sense. Impact of climate change on the infrastructure, right? So that's an issue, and you have been, I'm sure you have been hearing a lot about climate change from the White House to local newspapers, everywhere it is. So climate change is causing changes in temperature and rainfall patterns. Infrastructure components are designed according to historical records. So if you look at 30 years, 50 years of data, we have an average and standard deviation of maximum rainfall, and we do it on the basis of that. So it is not capable of surviving the new things. So by the way, Rafat, I have up until 4 o'clock, right?
Yes.
Okay, so I will skip some things, but I'll stop at 4. So let me show you the results of this thing. There is a.
We don't stop like sharply, but we tell people at 4 they are okay. They have to leave.
Okay.
But it's your discretion.
I need to leave now. I have a presentation.
All right. Yeah.
As I'm the presenter, so I should go.
Okay.
Thank you.
Sure.
I think this is very interesting. I also am more curious about bridges
They
and
have
stuff
nets.
too.
They
Like
have net
roads,
server.
maybe
Nets
about
in
roads.
server.
Roads, right.
They don't have it,
Mm-hmm.
so they can upload
What
their
is this?
own
Is this a
models.
road?
Right.
This was a road,
So
and
they
so
don't need for you.
Yeah,
It's like
We have nets and license.
something tiered.
Not nets.
Actually,
Nets
this is actually
is different from
uh,
nets and server.
a dam. actually.
Yeah.
So
This is what?
this is free.
Using
So
solar,
you're looking at an impact.
gives you the
So you're
option to
separating
upload
two
your
different
vaccine
parts of
models.
water. So one part
So
had high water,
to
one
convert
part
your
low water,
I
and
think
it
models
just
to
breached
vaccine,
because of the water.
and then you can
So this is
upload
like
them
a
on
dam?
the
This was a
server.
dam. So this was an impact.
That's separate.
Earthen dam.
You have to pay for that separately.
And there's a lot of those in the U.S.
Yeah. And many of them are maintained by the U.S. Army Corps of Engineers. Okay, so I think this thing is also. I'll just play with this, and at some point you'll be able to see it. But I don't want to spend too much time on this thing. Okay, so what's the interesting thing to look at is that once you start having roads which have a high rate of deterioration, and once you have a budget shortfall so that you cannot rehabilitate all the roads that need your attention, bottom line is that the mileage of roads that need your attention grows over time. Okay, and coupled with that is the fact that you have a change in annual rainfall, you have a change in seawater level, and then you have rate of increase in number of flood-causing hurricanes, so which is like category 3 or above hurricane, and then you have rate of change in maximum air temperature. All these things actually affect the life of your pavements. A pavement which is designed according to historical records, a road might survive 15 years, but if you have the climate change factors working, then they will probably survive 9 years or 10 years or 11 years. So that's an added stress on the infrastructure system. Let me move on, in the interest of time, show you some sustainability, and that's what I referred to earlier as as the fact that we need roads for development. But if you look at this simple fact, 15,000 tons of aggregates are required per kilometer of highway. It's a finite amount of resource. You could say that there are lots of mountains and hills, but at some point you do run out of them, and there are many cases where this has happened. So, for example, in California, now to make it profitable, you actually get aggregates from Mexico in barge. There are countries in Europe which actually get aggregates from other countries as well. For example, there's Latvia, former socialist US SAARC countries, and in countries like in India, you don't get aggregates within 200, 300 kilometers of your project in many cases. Here in the States, states like Florida has very bad quality aggregates, lime rock, for example. So they always get their aggregates from Georgia granite. And then in the Midwest, there are regions where you don't get good quality aggregates. So the procedure always has been you load up a truck with corn, you go to another state which needs corn but has good quality aggregate, you give them corn and get aggregates in return.
Backloading.
Yeah, but that's also drying out. So it is a terrible issue. And in this case, there is another model which I don't know whether I will be able to show you. Hopefully they will come up. 1 second. So what I try to do is I try to sectorize this. So there's a population and road demand sector. There's a construction and a road construction sector. There is also an economic sector, and there's an environmental sector. Let's go down. And it's a little bit a more involved model, and it's not a. To me, it's a complicated model, but you can certainly make it more complicated if you want. So there's an economic sector and there's an environmental sector, right? And I'm not going to results because you can imagine what's happening. So there are issues. For example, if you build more roads, you're actually cutting down the forests. And if you cut down the forests, obviously you are cutting down the trees, which means you are reducing the absorptive capacity of CO2, and then you're actually burning more CO2 because you are traveling and you're also constructing roads. So the net effect you can imagine is a reduction in the quality of your environment. Okay. So that's and if interested, I can leave this here. You can go to this website and take a look at the different results and things like that. The other thing that's pretty important is the flooding of roads, and I'll show you a quick example here. So if you look at a road, if you take a cross section through a road, when you're driving on a road, this is what it looks like. In general, there could be variations, right? So there's a surface course, there's a base course, there's a sub-base course, and there's a subgrade. So subgrade is your existing soil. And we put these layers on top of each other to make sure that when you put a load on the surface, the subgrade soil does not deform, because by the time the load reaches the subgrade soil, it has been distributed to a larger area, so the stress in that layer is very small. Okay. When you have flooding, you have things like that. What happens is, if you have a very thin surface layer, the water goes in very quickly and destroys the base course. And if the base course is destroyed, you have nothing to support the surface course, so the whole thing falls apart. Okay. And if you look at the structure of a road, this is the most costly component, because this has asphalt, which is like $500, $600 per ton. And the aggregates, which make up the lower layers primarily, are like $35, $50, $60 per ton. Still, if you don't have to factor in the delivery, the transportation cost also. Okay, so that's a critical issue. And what we have been doing is using system dynamics, trying to figure out what's the critical time period to cause the saturation of granular layer, and that's the critical time period for failure of a pavement. So Fred, we're talking about critical time period. So Fred is working on a very interesting project for resiliency of Logan Airport. In fact, Massport, they have different assets, and he is using system dynamics. And we are talking about critical time failure of runways, for example, or electrical systems. So this is in a small scale, something like that, that if you have a road, you know the road condition, you know the materials and everything, the age and everything, and you know that what is the depth of flooding and how long the flooding has been there. What is the time it takes for the road to fail? Why is this important? Because sometimes as a road authority, you have to make a decision after flooding whether to open the road to traffic or not to open the traffic. Because if you close it without any reason, you're losing money. People have to travel farther, people have to detour, there's a time involved, right? However, if there is a major problem and you cannot see it, in many cases they're hidden, and if you open the road, people die, that's a terrible thing, right? So what we are trying to do is trying to predict to this. And again, this is more like an object-oriented programming application rather than a system dynamics application. But there is a feedback loop. If you look at this effective permeability, thickness, critical time, particularly with the age and the mean annual air temperature, that actually affects your aging. So the pavement becomes very brittle and then it can crack. If it cracks, then it will, permeability or the water will go very fast, and that will affect its critical time. Okay, so that's another way of looking at this problem. So people have been looking at this through a spreadsheet or a single equation, and we try to look at this from a system dynamics point of view. And again, there is a model which shows this is what flooding can do. This is a road in Maine, northern Maine. Just cut away the road in half, and you can see here what's happening.
Steve, are you using these models for teaching?
Primarily teaching, and in some cases research. But
I mean, after the research, do you use it in class or?
See, the problem is I don't have any class or any module or any place where I can actually use these things. So Mike and I actually had a proposal to this education grant. So maybe coming up with some modules of civil engineering in system dynamics, or coming up with some system dynamics modules in civil engineering. So hopefully that will happen in future.
Cool.
But it's needed. It's needed. So anyway, you can see how it is coming in the picture. So a road is a living thing. It changes its properties every time you have a traffic going on, if you have a rain event, or cycles through the air temperature. So I think I'm running out of time, but I have one more. This is the last one. So this is a pavement slide, and if you look at this pavement slide, what I want you to show is what happens to a pavement if you do it in the right way, and what happens to a pavement if you don't do it right. So this is a picture taken right after a rainstorm, and if you look at the left side and the right side, you see a difference. On the right side, this is the open gridded not the right side, left side. The right side is a conventional roadway, right? And you can see there's a splash and spray, there's a glare, and driving is hazardous. You have seen all this, right? In the left-hand side, we have a special kind of mix called open graded friction course, which lets the water go through very quickly. And you can see there is no issue with glare or spray and things like that, right? So how do you actually design this kind of road and make sure that they remain functional over time? Keeping in mind that over time, the condition of a road always deteriorates because of traffic and environment. So this is why I think system dynamics is very applicable, because road is a very dynamic thing. Even though it is just lying there out there, not moving, it is changing. It is changing, day to day. So what we have here is, and I'm glad that this model is right here. I don't have to go anywhere. So if you look at this is actually a way of figuring out what is happening to the durability of the pavement right here over time. And if you look at these qualities that we have, noise absorption, permeability, rotting resistance, stiffness failure, and all these things. So noise absorption, this is also one critical thing. Many people live by the side of the highways, and you have to put up like big walls because you hate the noise. But if you have an open graded friction course like that, and there are many different kinds of pavements, but they are costly. They cost more than normal pavements. You can actually reduce the noise by over 50, 60%. Okay. So what happens is, because they have large pores or air pockets, the tire actually forces the air more through them than actually outside them. So you don't hear the noise if you're standing by the side of the road. So that's another example of use of system dynamics, because it's changing and there's a feedback loop. The condition of the road at any time dictates the response of the road at any time to the traffic and the environment, and vice versa. Okay, so that's, I think. So what I conclude is that SD can help us understand the importance of a problem, particularly over long term. The main causes, the solutions, and the better solutions and the best solutions we can probably filter out, and then it provides the answers that you've been looking for. But SD is not only applicable for CE, I think it's necessary. Otherwise, there are many questions that cannot be simply answered. Simply, there is nothing. So it should be made mandatory for CE graduates, and particularly for student projects like MQP projects. I don't know how you can work on that without looking at a system. How you can design the footing of a column which is going into a building, which is going into a part of an infrastructure without looking at the system. But that's the state of the thing. And this is an interesting picture. I think I should show you. This is a flying machine used to go from New York to Philadelphia in 2 days. At that time, it was the state of the art.
It's like the new road.
It's like the new road, yeah. So we may have to go back, unless you do something else. But this is Logan Airport, actually. So you can now go from New York to Philadelphia, Boston to whatever.
That's a flying machine.
Yeah, so I brought this up because I wanted to tell you that Fred is doing a very important work. Logan Airport is concerned that because it's right on the ocean, if there is a significant amount of flooding, then how prepared are they to make sure that you have the critical things going on, aviation things going on? At least they have places where they can land and like military aircrafts for supplies and things like that. So Fred is developing a model with different kinds of assets that belong to Logan Airport, East Boston, not Logan Airport, Massport, and make sure that you have a measure of resiliency. In other words, if a flood strikes, what is the chance that you will be able to be up and running within a certain specific period of time, considering all the implications and all the connections? Because, for example, if railway or MBTA is shut down or buses are not going, then you don't have the people who work in Logan Airport coming to work, so you cannot work in Logan Airport. If the electrical systems that are on in a building are actually flooded because of the water reaching that elevation, then you cannot power your generators, and then you cannot work. But that's all I have. So I thank you for your time and your consideration. And if there is any question I can try to answer, I'll be happy to. But I think we need to collaborate more and convince CE people that we need to have system dynamics in the curriculum.
We are trying to revive some undergraduate courses. In D-term, I'll be offering an undergraduate course with no prereqs. In the past, students have built their IQPs and MQPs on that course. We'll be next year offering 2 undergraduate courses also. And there's a need. A lot of students don't know that these are being offered. The population in these courses remains low, which gives an opportunity to cancel them and not offer them next time. So I think once there's a critical mass and there's word of mouth, we can offer more of these. We have capacity to offer at least some undergraduate courses. There was a lot of information there. And for me, it was like drinking from the hose. So, and I think you have done in particular domain a lot of work. There's probably a room for a book there, or possibly a course at some point.
Sure.
But I mean, to me, it's like preaching to the choir. If you're telling me there's a need.
Right. Yeah, I always tell students who they come for SSPS courses or social science courses. They say, "Can I take economics and things like that?" I said, "You can certainly take, but do consider that there are courses in system dynamics also. Why don't you consider those?"
And they meet social science requirement, and they also prepare you for your projects.
Right. But I think that unless people realize they prepare you for the projects and they help you in some sort, they always think that it's like by 2 things, checking off my my audit sheet and I'm done. That's a sad thing. But I hope people take. I'll be advertising your courses. I'll be telling students to go and take these courses. That's part of my job. But I hope people realize. Do you have a lot of civil engineers participating in your SD conference that you have every year?
Yeah, there are people who come in. There is a guy named Stephen Ogalnana. I don't know if he was my colleague at Asian Institute of Technology, but now he's in Scotland. And he is a chair of I think, built environment department, which is like civil engineering and planning. And he's sort of totally, he was a construction, his sort of concentration was on construction engineering. He has done a lot of work in civil engineering. Last year, I had an invitation to write for the International Society for City and Regional Planners. It's based in The Hague, and I sent an article in. And this is about urban dynamics as a planning model. I don't know if I shared. I think I shared it in the course.
Yeah, I think it's
and there are some schools, I think, more abroad than here, which are into system dynamics. For example, for water resources planning, hydrology. It's great. I've been trying to collaborate with Paul in your department.
Yeah, but Paul is like he has IQPs to deal with and MQPs to deal with, and
so he's just too busy.
He is stressed out thin like everybody else. But you're right.
But
his area is
hydrology is stocks and flows.
Yeah.
We use that analogy anyways.
Right.
I'm curious, Rajib, to know, where do you publish such research that involves system dynamics?
So there's one publication for looking at sustainable roadways using recycling in resource conservation and recycling. It's an Elsevier publication, resource conservation and recycling. And then the flooding one went to, there's a Journal of Flood Management. It's UK based. I think it's also Elsevier. And then there is Transportation Research Board. So we don't have specifically like a systems-based thing for civil engineering. There might be, I don't know.
In transportation, there is Fukuda at Sushi Fukuda in Nihon University in Japan, who does a lot of system dynamics.
That's right.
Transportation.
That's right. I think UK, Canada. I've seen authors from Canada. I've seen authors from UK and Japan who are civil engineers and who work with system dynamics, but not so much in the US.
Yes. And did you participate before in this system dynamics conference?
You know, every time it happens, I'm outside the country. That time in June, it happens, right?
In July.
Yeah.
In
I
June,
think
July.
Professor Masher, he also worked.
I mean, did you
in
submit to
this
the
area.
conference?
No, I never.
Not even.
Yeah, you
Because
see
I
what
think this is very
Yeah,
There are sessions on infrastructure, I recall, in the conference.
Yeah.
So
yeah. I think my models will be very rudimentary for system dynamicists. It is unique for civil engineers, but I fear that they are not very system dynamically, I don't know if it's the word, correct. What I try to capture is the essence more than looking at the numbers.
Well, you in the domain, you have more knowledge about the problem.
Yeah.
So no system dynamicist, howsoever expert he might be, can translate that knowledge better than you can. So I think
Small
you can bring a
models.
lot into.
Yeah, the world of small models can be very powerful, even for very complex problems, right? That's we've heard many times in the coursework in the SD program. So I think it's no different in engineering disciplines. You can do a lot with fairly parsimonious models.
One thing, I that's the way I have been trained. I don't want to take much time, but I just want to mention that the way we have been trained since our graduate studies as civil engineers is that publish where there is funding. Don't publish anything where there is no funding. Publication for the sake of publication and scholarship is not welcome. I know that's a wrong statement. That's not a good statement.
No, but that's the
real.
truth.
That's the real. That's the truth.
That's the reality.
So that kind of prevents me from going out and submitting anywhere rather than places. But sadly, what's happening is that, as Fred could tell, people who are in charge of funding in civil infrastructure systems, in most cases, get terrified when they see a system dynamics model and the need for data that will go into these things. Something needs to be done. Number one probably is to replace as Mike always says, we don't want to show the bathtub and the faucets anymore because that turns people off. But I think that's a point. But if we somehow can simplify further for civil engineers, they will probably be more attractive and they'll be more receptive to the idea.
Well, there's a way to build a model hierarchically and show a top layer or sort of a middle layer,
right,
which is more understandable than the stock and flow level.
Right.
And it's important to adapt for the specific audience.
You're right.
Thank you very much.
Thank you.
This is very enlightening.
Thank you.
and we have
Thank
a
you for
topic for a future CLM.
There you go.
Yeah.
We'll get you
Sign Fred up.
we'll come back and do a tag team presentation on Massport.
Cool.
Yeah.
Thank you very much.
Fred, you better get your laptop because that's a huge model.
Well, actually,
Yeah.
I'd love to have one of those big screens like you got in the conference room over there in Pavement.
Yeah.
That's
Thank you.
to have one almost as big.